Good evening. Let us wait for some time. So meanwhile, people can join. Yeah. Good evening. Let us start. So before starting, I would like to appreciate that you are attending the lectures. So I hope you are getting benefit from this. And if you have any doubts, you can ask. You can interrupt in between, and you can ask, or you can just put in the chat. So. So this is the third live session on this manufacturing process, casting and joining, which is taught by Sonu Kumar Chaudhary. Myself, I'm Rakesh. I'm a PhD scholar at IIT Bombay. So I'll be taking a brief overview of this session, this whole entire week. Then I'll be solving some new questions on that. So let us start. Before starting, I would like to, yeah, yeah, give me a minute. Yeah. So first, I hope the screen is not. Yeah, yeah, yeah. It is changing now. So you'll be able to see some recap. So here I have presented. Uh, okay. Oh, so actually, there is some delay between my slides as well as the presentation on the screen. So yeah. So now we are seeing the recap. Yeah. I think there is some problem with this. So I will switch back to my original thing. So yeah. So initially it will be recap. So these are the different topics that was taught during this week. That is week three. These are multiple. So I will just read out. So one thing regarding the permanent mole casting and die casting, and then different types of casting such as centrifugal casting, continuous casting. Then we briefly gone through the cost analysis of casting. Then we also started the joining process of such as welding. So then we discussed the physics and the principles of fusion welding, and then different types of microstructure present such as heat affected zone. And then we just like briefly work on the solidification of weld, or else, in other words, the what happens during solidification of this localized region that was milled during welding. So these are the different recaps. So I will discuss one by one. So starting with the multiple mole casting, that is, so basically we have two types. One is expendable, in which the mold has to be broken, and then we have permanent mold casting, in which the mold is made of some metal. Then it can be reused to many times, and then production rate will be very high in terms of in permanent mold casting when compared with expendable. So in which we are expending this mold, such as sand casting, you have to break the mold. Investment casting, you have to break the mold. So it also pattern will lead to dimensional property variation in expendable mode. Later on, you will see what is the accuracy that we get with different types of castings. So let us see the permanent wool casting. So permanent wool casting, as I discussed, it is made of some metal. Here, it is made of graphite. So you see this graphite mold here. Okay, this graphite mold, and this is the mold, and this is the part that we are going to that we are going to cast. So basically, what we do is we have a airtight chamber in which air pressure we maintain some pressure. Then we have a plunger. We just pull out the pressure out so that this molten metal will grow through the refractive pouring tube and it will fill the castings. Once it is solidified, we'll take out and we'll trim it and we'll send for the further process. And we can use, since this graphite mold, we can actually cast very high temperature metals as well, and we can reuse this mold any number of times. So this is one type of permanent mold casting in which we are just using a plunger to pull the to suck the material into the casting cavity. Okay, this is one permanent mold casting. Then so let us see some brief overview of this permanent mold casting. Mainly, molds are made of steel, generally, or cast iron. The cavity with grading system included is machined into two halves, provided accurate dimension and good surface finish. So basically, in permanent mold casting, this I can say a kind of disadvantage. We go for simple parts in which actually we can open it and we can remove it. Means we can open the molds and we there should be a available provision to take out the casted component, and we'll get a very good surface finish since it is the metal. So whatever the surface finish of the metal we actually can get, so around some 2 micron surface finish we can get on using this metal surface when compared to sand casting, in which we use around some 6 we get around some 6 micron surface finish. Then generally we cast aluminum, magnesium, copper alloys, rarely cast iron. in which we have to go for very high temperatures. And then if there is a need, then the cores also made of metal. Uh, Sometimes it also be made of sand as well. Okay. These are the different types of permanent wool casting. Then yeah, I'm saying if you are using sand cores, then we call it as a semi-permanent mold casting. So one thing is we spray some coatings such as boron nitrate sprays, which facilitate an easy removal of the cast component. So there will be no fusion between the dye uh, at the mold and the cast components. So that's why we use some coatings, and these coatings also helps in heat dissipation and lubricate surfaces. Then let us see one simple actual uh, procedure that we followed in permanent wool casting. So in step one, that is step one, so we just spray the nozzle, which is mold releasing agent or heat dissipation agent. So this is in. So there is the system is continuing. We just took one instant. What is happening? So we just uh, uh, we let the dye cool down, then we spray the nozzle, then we close, then we apply some pressure to close the nozzle, then we pour the metal and we wait till it solidifies, then we remove the component. So here there nothing is shown. Generally we will have some ejector pins which will eject the component out. Yeah, just a second. Yeah, okay. So this is a simple permanent. Also, this is I will discuss what type of mold casting it is. So this is permanent mold casting. Basically, we have different types in permanent mold casting as well. So these are the advantages of and limitations of permanent casting. So as I mentioned, there will be a good dimensional constraints and more rapid solidification. So finer grains are produced. So the strength of the component will be more. But limitation is that low metals only can we can use and simple geometries because we have to open the dies and we have to take out the component. Of course, it is associated with high cost of mold. These dies generally they are costly. So if there is any design change, then it will be difficult for this permanent mold casting. So some of the application is when there is requirement of high volume production. We should not directly go for permanent wool casting. We have to see the volume, then only we have to go. Otherwise, we have to start with the sand casting because it is like cost effective. And some of the components are some automotive pistons, pump bodies, casting, aircraft missile, and etc. These are some of the parts that are typically made by permanent wool casting, and these are some of the alloys that are used during permanent wool casting. So let us see. So now comes to the die casting. So basically, there are in permanent wool casting means we are just making the mold, and we are not applying any higher pressure. We are applying very limited amount of pressure, as you can see here. We are applying limited amount of pressure, as you can see here, as we just pulling the plunger out. So but when you say die casting, so we generally we work around 7 to 350 megapascal. uh, I hope this is not changing. Yeah, I think you have to see die casting. Just wait, let it come. I think I will log in again. Yes, yeah, I think now you can see. So, so in die casting, whenever you use the die casting, it's a kind of permanent mold casting in which we work around 7 to 350 megapascals of high pressure. Then, so as you see, high pressure is maintained during solidification, then the mold is opened and the part is removed. All the process remain the same except we are using very high pressure during solidification. So these molds are typically made of metals, and we call them as dies. Hence, this the name die casting. Okay, so we have basically there are two types in die casting. So high pressure of to force the metal is what distinguishes from the other. So we are using high pressure to force the metal into the cavity. So we will discuss what is the thing is. So die casting machines. So basically we have two types. One is the hot chamber and the cold chamber. Here, what you see on the first figure is the hot chamber, in which the chamber entire chamber is inside, and the plunger so the when the plunger is moved out, so the liquid comes in. When the plunger pushes it, means moves down, then this liquid enter the cavity, and then the mold is released, and then cavity is taken out and trimmed. Okay, this is the hot chamber in which we have kept entire chamber inside. Means we have plunger system, everything we have kept inside the chamber. But when you come to the cold chamber, as you can see on the right side, so we are just taking a ladle, we're just pouring the metal into it, and we are just pulling with the ram. Okay, and then is entering the component. So these are the two different. So in hot chamber, the entire chamber will plunger system, everything will be inside the molten metal, whereas in cold chamber we separately bring the metal and we just enter, and if you pull the ram to push the metal into the cavity. So this is the difference between hot and cold chamber. So now let us see what is the difference, actual difference between that is the process. Let us see the differences now. So the basic principle remains same. So metal is melted in a container and the piston injects the liquid metal under the high pressure. But when come to the cold chamber, molten metal is poured into unheated chamber. Okay, and then from external melting container, and the piston injects the metal at high pressure into the air cavity. So as we understood in the process, then high production rate, 500 parts per hour, but it is not usually as fast as chamber. The only reason being there is an additional step, that is we have to bring the metal and we have to pour, then we have to push the ram. But in hot chamber, we just have to pull out the plunger and push. So there is limited number of operations in hot chamber. Then, but in hot chamber, generally we use low melting points such that our plunger is not attacked chemically, but at higher temperatures. But in cold chamber, we can go for high temperature metals such as aluminum, brass, magnesium alloys. So some of the examples are zinc, tin, lead, magnesium. All are below 470 degrees Celsius, not more than that. So that's the only advantage in hot chamber. In cold chamber, we can bring the metal from outside, and then we can. The entire process remains the same. That's the differences between these. Then let us see the advantages. So large production quantities, good dimensional accuracy, and then thin sections and rapid cooling, so finer grain and high strength. Okay, these two are like these two are like connected. Then disadvantage with the only we work with the only low metal points, metal low melting point metals. Then part geometry should be simple so that it can be removed from the cavity. Okay, so that is the main advantage and disadvantage of this die casting. So we just revised what is permanent mold casting, and then we came to die casting, one which is the kind of permanent mold casting. So now let us move to the other types such as centrifugal casting. So as the name signifies, we use centrifugal force to distribute the metal. As you see on the right side, this is typical centrifugal casting, which used to produce large cast iron pipes. So this is the end view and this is the side view. So this drum will be rotating with the help of the support rollers, and the molten metal is poured, and it will be distributed at the outer walls due to the centrifugal force, and then solidified and then taken out. So this is very simple operation uh, when compared to the other steps. So let us see different types of centrifugal casting. So this we already discussed, typical centrifugal casting. So we have other type, that is semi-centrifugal casting, and then third one is centrifuging casting. So in the second type, so basically we are using a sand casting inside. Okay, then we are pouring metal and we are rotating it so that the metal is evenly distributed over the entire part. That is why it is called semi-centrifugal casting. Then in the right side, this is centrifuging casting. So basically, it is a combination of investment casting. So actually, we have two parts with the central screw, which is apply the metals to the material, molten metal to the component. So that's why it's called centrifugal casting. So we can keep many number of different types of cavities, different geometries with the central screw, and then we can rotate. So this is the all about centripetal casting. So the final one is the continuous casting. So this is typically like direct casting, in which if you want to produce a big billets or railway lines, very big billets, we can directly. There is no such mold that is required for cooling, and then we break the mold. No such thing. So that finally we will take a ladle in which we'll pour the metal into the tun dish, and we have a molds made of copper generally, which gives approximate shape to the liquid. So the it will be liquid state. Then so we have some discharge rags and guide rolls, which will still it will be like not completely solidified, but it has some little bit shape. Then it was passed to these pinch rolls. Meanwhile, we have a water space here which cool down it a bit. Then we have pinch rolls which actually can have some drag and it will drag out. Then we have these curved guides. Then it will come to the straightener. Then reheat furnace, sizing mill, and then cut off. So this is the process of continuous casting. You can watch some nice videos on this, which gives a good clarity on this. Then comes to the cost analysis. So I will just briefly discuss cost analysis and casting. So in this cost analysis, we are taking care of every single operation that is involved. Okay. So let us see the terms. So yeah, any doubt? Okay. So let us see the total cost of casting involves includes all costs, both direct and indirect, that result from the design, production, distribution, use, and salvage of the casting over its lifetime. Total cast. So it is considering each and every aspect from the start of the casting to the end of the product. So everything is taken into account. Nothing is discarded. So this cost is given by CT by N, which CT is nothing but total tooling cost, such as pattern, core blocks. We will see how it is calculated. Then N is the lifetime number of castings. CC is the cost of coring. V is the total casting volume. CM is the alloy cost. C naught is the casting equipment and labor cost, and T cycle is the total casting lead time. We'll see how these are calculated. Y is the yield. So defectives are discarded, then the rest uh, is taken into account. This can be like the sprue gating system also not actually helping. So this also can be included in this yield. Then cost of the secondary process such as machining, finishing. So this is CS. So let us see how each term is calculated. First thing is total cycle time. So total cycle time is nothing but non-productive time. So let us see. It is important to note that total tooling cost includes all costs associated with the tooling, including the cost of pattern, core box construction, cost of producing and inspecting first article, and cost of iteratively modifying the tooling to meet the specifications. Also, material volume includes not only the volume of the casting but also the volume of the risers, runners, and screw used to the feed in the casting. So this is how the total cycle time tooling cost is calculated. Before that, let us see the total cycle time. T cycle is nothing but sum of the non-productive time, mold build time including core replacement, time to pour the casting, time to cool, and then remove the gates and razor, etc. So every time is actually included, which gives the total cycle time of each component. Okay. And then I missed one thing. So basically, we calculate this per unit basis. Okay, per unit. That is why we are always dividing by n number of components, and accordingly, the all other things are modified. So this is the total cycle time. That is this. Then cost analysis of the casting. So this is unit cost of the coring. So if at all we are using any core for our analysis, then this is how it is used. So it is so since it will be numbered, so it is given I is equal to 1 to NC, and is the number of cores, volume of the core material multiplied by cost, core making equipment labor cost multiplied by total make cycle time divided by the yield. So this is how the coring cost is involved. Coring is not what the core type cost of making cores. So that is CC. Then we have cost units of the casting, the secondary cost, such as machining, heat treating, welding, parting, planing. So all these are involved in a secondary processing cost. Okay, cost of secondary processing. You see this. which is it is also summation number of secondary process, that is ns. CD is the secondary process tooling cost, secondary process equipment and labor cost, which is divided by secondary process yield and multiplied with the total cycle time. Okay, this gives you CC, CS value. Okay, I hope everything is included in this. So this is how you calculate. So finally, you have cost is nothing but CT is the total tooling cost. Uh, then we have N, we have CC, we have CMV, we have every each and every value of this. So it is very so in any question, it is simple mathematics. You can figure it out easily. So this is how cost analysis is performed. We are taking care of each and every component. We are not leaving anything. So the main goal of this cost analysis is to minimize the tooling cost, to minimize the material cost, to minimize the process cycle time, to maximize the yield, minimize the number of cores and secondary processes. So this is the main goal of this cost analysis of the casting. So let us see economics of machining. This is very interesting. This will some of the discussions that we had so far. So let us see. This is cost per piece on the y-axis, which is relative, and then on the x-axis we have number of pieces. Let us start with sand casting. Okay, initially the value is decreasing with respect to the number of pieces, but later the slope is almost constant. Okay, not changing much. Okay, so that is the sand casting. The cost is not more or less similar after certain number of say some thousand, hundred. Okay, but when you go to plaster cast, in which we can use POP or plaster of Paris to do for the same process. It is also same. Initially it is decreasing, but later it is a little bit constant. But when you see this permanent mold casting, it is drastically, the slope is drastically decreasing with respect to number of pieces. It is decreasing so with very high rate. Okay. And then if you go for die casting, which is the highest, which is giving you the least amount of cost when the number of components are increased. So this gives an idea in which process should I select. So it which based on the number of pieces. If you want very high volume, go for die cast. If you want low volume, go for sand cast. So this is the upper and lower limit. We can select the middle according to your requirement. This is very interesting economics casting. So let us see one of the important topic in casting, that is casting defects. Okay. On the left side top, you can see the Mistron effect, which in which the mold is not completely solidified. So it solidified prematurely. So it did not heal the mold cavity. So the reasons can be the fluidity of the model, low pouring temperatures, low pouring, and thin cross sections. Thin cross sections, there is a chance it solidifies prematurely. These are the different reasons for the Mistron. Okay, one. So let us see the second one, that is sand blow. So basically, when you pour metal into the molten cavity, so there will be some binders which will vaporize when it comes contact with the metal, and then these gases has to be vented out. If they are not vented out, it forms this sand blow. Okay. So the third one is the cold shed. So cold shed is if there is when two streams of metal. So when you pour the metal, it will enter like this. It will enter. Then after some time, it will enter from this. So there is two streams coming. So they will not get fused properly. Okay, due to premature freezing. So this is called cold shed. So there should be an interface whenever you see this cold shed defect. If there is a question, so if there is any two surfaces, if there is no good fusion, so that defect we call as cold shed. So on the fourth one is the cold shorts. So which is occurring due to the splattering of the liquid. So maybe the velocity of the liquid is too high, so such that there is splattering and which forming solid globules. Globules means uneven pores, you can say, and then it's collected at the which will be entered within the mold, and there is no chance for it to escape. So they will be inside the casting, which is not good for the casting. So these are the different types of defect. This may be present in the casting and may not be present in the casting, but we generally see different types of defects in it. So continuing, we have shrinkage cavity. So basically, this will not be correct way to represent shrinkage cavity. This will be the correct one. Okay, if you take a cylinder and if you cover all the lateral surface area and the bottom surface area, so the solidification start from the surfaces and the bottom. So as it's solidifying at the center, so the liquid at the top will be supplying the metal for the shrinkage. But at the top, so as you see, this metal is supplying liquid to this and this. So you can see easily from the top there is no solidification from starting. So that is why we are seeing a shrinkage from the top. Okay, since the liquid is evenly supplying to the all the surrounding solidifications. That's why we see. Suppose if at all, if there is the top portion is also there is a sand, then you see that shrinkage at the center. So this is also called hot spot. Wherever we have a hot spot, there is a chance that the shrinkage can happen at that hot spot, because that is the only point being liquid, the final material that is going to be in liquid state. So if it is in liquid state, then it will supply material if there is a shrinkage. Okay, so that is the shrinkage cavity. Then we have small voids, fourth one. This can be of so many reasons. One reason is, as we discussed earlier, this splattering or globules are the sand blow. Then basically in alloys during solidification, there is a chance that shrinkage can happen. Okay, localized shrinkage. Okay, while solidification happening, there will be some gaps between the solidification features, which can result in this small microporosity. Or else you can see one other way to see this microporosity is that liquid has good gas absorption. For example, like hydrogen, nitrogen. These gases are very highly absorbed when the material is in liquid state. But when it is getting solidified into solid, this liquid try to escape. But if there is no good venting facility, these bubbles will be like inside the uh, casting. And this also can result in this microporosity. Okay, that is one small void. Then fourth one is the hot tears, which generally occurs if there is unyielding support. So in this figure, when it is solidifying, there is a chance that it will pull. It's, it try to shrink while solidifying. If there is unyielding support, then there is a chance that it can form these hot tears. Similarly, with the pinholes, just the holes are similar, which are so basically mainly pinholes occur during this hydrogen porosity. So we can see small holes at the near vicinity. Okay, then we have three, four, five, six, seven, and then we have eight, which is sand wash, mainly caused due to the high velocity of the mold, which can erode the surface, and then or it can the loose sand that can actually fall into the casting. Okay, that which calls scab or sand wash. Okay, and then we have ninth, which is called as a penetration. So if the mold is not, if the molten metal is of very high fluidity, or if it is heated very high, the viscosity will be very less. It can penetrate into the sand. Okay, that is like penetration. On the right side, you can see this is called mismatch. So actually, cope and rag are not matched perfectly. So you see this offset in the casting. Then we have the final one is crack. So these are called cracks. So basically, when the mold, if it has does it could not have the good thermal deformation, it can form cracks in the mold itself, and this fluid can molten metal can actually go into the cast and then form these cracks. Okay, these are the different types of casting defects. We'll just go through. One is the Mistran, sand blow, cold shed, and then we have this solid globe cold shots. Then we have shrinkage cavity. Then we have microporosity. Then we have hot tears. Then we have pinholes. Then sand wash, scab, penetration, and then mold crack. Okay, these are the different types of casting defects. You have to actually remember them. Maybe they might be asking you in these casting defects as well. So that is all about the casting defects. So we are at the end of this casting process. So we have to see these product design considerations. So basically, we have to see that geometry should be geometric simplicity. So while designing any component, we have to take care of this process as well. Then we have to see the corners if there is, because these are the sharp edges, so there is chance that uh, the bolt can actually erode. Okay, sharp corners are very difficult. Then if it all, you can provide some fillet round edges to avoid that. Then we have drafts to easily for easy removal of the pattern. So this all this you can consider while designing the component itself. Then we have two shrinkages, avoid this type of cross sections. Actually, you can provide a core to avoid it. Then use of cores, we have to limit the use of cores. So here, this is the one design in which you are using core, and this is the same design in which you are not using core. Okay, so this is a design facility. Then we have to see for the dimensional tolerance, surface finish, meshing elements. Accordingly, you have to select the type of the process as well. Okay. So this is all about the casting. So by this we completed the casting process. So this is like a brief on casting process. Even there is much to learn. So if you are interested, you can go through the references and see. So let us start with the joining process. So let us go ahead. So basically, joining process is not only this welding process. There is mechanical joining as well, in which we can use nut bolt or we can use rivet also. But we mainly focus on this welding, and we have other types as well, brazing and other types. But we mainly focusing on welding, and we'll cover the others a little. Okay. So let us see what is welding. So joining process in which two or more parts are coalesced at their contacting surface by application of heat or process. So coalesced means combining two into one single entity. Okay, using heat or pressure. Okay, we can actually apply heat or we can actually apply the pressure as well. So many welding processes are accomplished by heat alone with no pressure. Others by combination of heat and pressure. Still others pressure alone with no external heat at all. We'll see the classification. When you see the classification, you can come to a decision, or you can understand how this is useful. In some, you can use X pillar if the building space is too much. So filling by themselves will be difficult. In that case, we can actually use filler to fill it. Okay. So let us see. This is a very nice mechanism of building. Let us focus on the left figure only. So let us see the bonding. So one figure is seeing bonding force, other is the binding energy, the x-axis is separation. Okay. So if you see, if two atoms, when you try to bring them into very near entity by applying heat or by applying some pressure. So if you have two atoms, they are coming closer. So this atom will have electrons, this atom will have electrons. But when you bring them very close, the nucleus present at the center of each atom will actually attract the electron clouds of the other atom. Okay, so there will be attraction force developing. But when they come sufficient enough, so these electron clouds of the two atoms, like there will be electron clouds here, there will be electron clouds here. Okay, they will try to repel. Okay, but there will be a separation distance in which both will balance. This attraction and repulsion force is actually balanced, so that we call okay, that is the like neutral point in which we can actually establish a bond between the two atoms. So that is brief of this mechanism of welding. So how we bring the atoms, it depends on different. So we basically concentrate on how we are going to bring these atoms together. So as you see at the second point, equilibrium placing, the net potential energy is minimum. The aggregate atoms are stable and the atoms are said to be bonded. Okay, I hope you understood this simple mechanism. So if not, I'll just draw a diagram. So let us say this is one atom which is positively charged inside. This is one atom which is, this is nucleus which is positively charged, and then we have electrons. Okay, I'm drawing roughly. Then we have other atom as well, which is nucleus at the center, which is positive charge, and then we have electrons. So I'm just randomly drawing. So now if you see, we have these electrons. Okay, these electrons will be attracted to this nucleus. Similarly, these electrons will be attracted to this nucleus when they are coming closer. But when they come sufficient enough, then these electrons will repel. Okay, so this is the repulsion and then attraction forces, and they will balance at a point which is called equilibrium point, and then we said they are bonded. That is the basic understanding behind this welding. So now see, let us see the classification. So as you, if you remember the first slide, we tried welding can be established using complete melting, only heat source, heat and pressure, and only the pressure. So this is how this is like spread. So one is the solid state welding. Coalescence results from the application of pressure alone. Okay, no filler metal is used. This is also called diffusion welding, friction welding, or some of them are diffusion, friction, and ultrasonic welding. This is called solid state welding. The second one is liquid state welding, in which we actually apply heat and we completely melt both the materials. Filler can be used which are same as metal. So some of the examples are arc, resistance, and gas welding. Then we have finally the solid state welding, in which we apply is used for joining metals which cannot be withstand high temperatures. Contamination to is removed partly by mechanical and chemical cleaning and partly by heating, which are brazing and soldering. So we will discuss this solid state welding. So basically, we are not welding two entities. We are just keeping the two entities together, and we're just soldering, in which the solder actually holds these two together. Then we have adhesive bonding and mechanical fasting. These are the other types of joining process. Okay. Then let us see the power density, which is an important term. So power density is nothing but the amount of power that you are applying per unit area. So if you see oxyacetylity flowing, we have 10, and if you see the electron beam, we have 10,000. Okay, it is increasing while you go decreasing. Well, you go from top to bottom. Arc welding is 50, STM welding is 1000, laser welding is 9000, electron beam welding is the highest. So basically, what happens if you have a small spot in which you can focus very high amount of energy, there is very less time to like conduct this heat into the base material. Okay, but if you have a larger like power density, so actually you are heating the entire surface area, so there is a very good chance for conduction. So basically, if the all the amount of is going with conduction to the parent material, so it's very difficult to weld the two components. So that's why selection of power density is very important. So let us start with the first one, that is the fusion welding. Then we will see the other types. So a fusion welding process used to melt and fuse the base metals. The most important factor governing fusion welding process are the heat source characteristics, the nature of deposition of the filler material in the fusion zone, which is known as weld zone, then heat flow characteristics into the joint, then gas metal or slag metal reaction with the fusion zone, and then cooling in the fusion zone. Cooling, residual system, and metallic changes. We'll discuss all these 5 points one by one. So first one is the heat source in fusion zone. So what type of heat source you can use? So one is electric arc, chemical flame, or exothermal chemical reaction, or electric resistance heating. So electric car you can directly use, then chemical flame such as oxy fuel gases. What is the common is oxyacetylene gas. Then we can actually go for thermit welding as well, in which exothermic chemical reaction will happen. Then we can go for the resistance welding, in which we use electrical resistance for to heat the metal. Okay, I will discuss each and everything. Then it will be clear for you. So let us see. So I have kept two types side by side so that you can understand easily. So on the left side, you see some fusion welding process. On the right side, you can see some solid state welding process. Okay. So initially first one is the arc welding. Okay, melting of the metal is accomplished by the electric arc. So these are all fusion welding processes. So the second one is resistant welding, in which welding is accomplished by heat from resistance to an electric current between the flaying surface. Okay, if you see two surfaces, and if you apply some heat potential, so if there is any small air gaps, so there is a chance that resistance due to that resistance, the heat is generated within the vicinity, and then that heat is actually helping to join the these plates. So generally, we use resistance welding for small for joining the sheets together in automobile or any other sheet industries. Then finally is the oxy-fuel gas, in which we use very torch, you can say, oxy, such as acetylene torch, to melt the two joints. So this is a simple lap joint. So if you want to melt, we just melt the center portion, and as we go further, uh, the weld pool will move, and then it will create this bonding to the between the plates. So that is the oxy gas welding. Okay. So on the right side, you can see the some of the solid state welding process. One is the diffusion welding. Coalescence is by solid state fusion between the two surfaces held together under pressure at elevated temperature. So this is simple. This if you guys know about sintering process, so the same principle is used. Means I not sintering. Basically, we'll take two solid surface, we'll keep them together, we'll apply some pressure, and we'll keep inside a furnace. Okay, this is how fusion welding happens. So we are using pressure as well as at high elevated temperature. So there will be no actual melting happening, but due to the separate pressure and elevated temperature, the bond is established between the surfaces. So next one is friction welding. So don't be confused with the friction welding and the resistance welding. So coalescence of by heat of the friction between two surfaces. Okay, I hope this is a very important topic right nowadays. So we'll have a two plates like this, and then we have this friction pin actually at the center, and it will be rotating. Okay, and this pin will be moving along the surface. So basically, it is not actually melting; it will just very high strain rate deformation happening at that point, so that metal actually mixes together in semi-solid state, and it will the bonding is established. Okay, friction welding, which is very good process if you want to join two not of the same material but two dissimilar metals can be joined using this friction welding process. Then comes the ultrasonic welding. So coalesce by ultrasonic oscillation motion in a direction parallel to the contacting surface between two plates held under the pressure at the release. So it's very simple. We'll take a plate and we'll take one more plate, which is this is a simple lap joint. So we'll put a ultrasonic transducer or probe, and then we will there will be some vibrations. So these plates will be vibrating here and there, and then you are going to get this bonding between the plates. Basically, we use this for battery plates that are joined. So there is one application for the ultrasonic welding. This is simple, and we can use this ultrasonic in many ways as well. Even in the friction welding, this is one case. In other case, we can have a two shafts. If you want to join two shafts, we can initially held together. We can rotate this shaft, keeping the other one constant. So there will be heat generated, and then at an instant we can just apply some pressure to bond, and then you can stop the machine at that instant. So this is used for the joining two shafts as well. So these are the different types of fusion welding as well as the some solid state welding process. So let us see the comparison between these welding process. So oxy-fuel gas welding develops large amounts of heat, but high heat density is relatively low because heat is spread over the large area. So that's the case. So that the heat temperature is around 3,500 degrees Celsius. So oxyacrylic gas, the hottest of the this oxy-fuel gases, and we have different types as well. Here we have oxidizing flame, carburizing flame, neutral flame. Okay, so based on the color, that is red, yellow, and blue, red, yellow. Okay, so this depends on the temperature that is being. So the basic disadvantages when you use the oxy fuel gas, it has a very low heat density. That means the heat is actually spreading into the parent material, which is not good in some aspects. We'll discuss that why it is not good if heat is spread into the nearby surroundings of the parent material. When it comes to the arc welding, the heat higher energy over small area. That indirectly the heat density is very high. In arc welding, we have seen around 10, I guess, arc welding around 50, which is 5 times better than oxy fuel gas. And the temperature produced is 5,000 to 6,600 degrees Celsius. So this is the heat density, which is known as power transfer to work per unit surface area. If the power density is low, then melting never occurs. If the power density is higher, it can vaporize the metals itself. So there is a we should use a practical range for heat density with which welding can be performed. Okay, this is about the heat density. So this is a typical cross section of a weld joint. On the left side, you can see briefly. So we have a fusion zone, and we have a heat affected zone, and then we have an interface as well. Here, this is the interface, fusion zone. So this is generally interface, and then heat affected zone. So basically, this also called as weld zone. Okay. Then on the right side, you can see the actual microstructure. Zoom it a bit. Okay, at the center you see these columnar grains, and at the interface you see these coarse grains, and then as you move far away from, you'll see finer grains, and then original polymer grain. Okay, this is how the microstructure is very. So studying this is very important because the properties on each region is different. Basically, the properties, if you see structure property relations, so it varies. This gives a very good example of that. So let us see what happens in heat affected zone. So basically, the metal is not melted completely, but it has exposed to high temperatures, so that there is a microstructure changes in the microstructure changes in the solid metal. Then chemical composition same as base metal, but this region has been heat treated so that its properties and structures have been altered. Okay. Effect on mechanical properties intersection is usually negative, and generally you see these welding failures occurring at this heat affected zone. So studying this will be very important for us. Okay, let us move forward. We'll see solidification, solidification of the weld. The final topic in this session. We'll see. So how the solidification is actually happening. So basically, it happens in the effects related to cooling is three types. One is the contraction, residual stresses formation, and metallurgical phase transformation. So the contraction happens because so if you see this joint, we have a molten pool. So from this edge and from this edge, the solidification happens inside into the that center node. Then what happens due to shrinkage? This metal is being supplied, and then at the center you see this pipe, which is like incompletely solidified. Uh, After completely closing, incomplete region is happened. You can see that is called pipe defect, which is a complete contraction of the liquid. Then we'll see the residual stresses. This is very interesting. If you see this figure, so you see these tensile stresses in the weld and then compressive stresses in the weld. So basically, what happens? So this will be a very hot region, and this will be at room temperature or room temperature. Okay, this will be molten initially. So what happens when it is trying to solidify? It tries to contract. So when it try to contract this, whole region is getting expanded. So that's why we are getting these tensile stresses in the weld. And then a little far away, due to these tensile forces, there will be compressive forces induced in the metal as well, in the parent metal as well. So this is the counter effect, I can say, so that the component is stable. This is how the residual stresses form. This is not beneficial because this can like deteriorate the mechanical properties of the weld joint. So if you see, so one example given by the professor is, if you take very high costly glass and if you take very cheap quality glass, when you drop it, this high like low quality glass will shatter into small pieces, but high quality glass generally it should not be broken, or if it is broken only two three the pieces are very less, like broken pieces. So the reason being that this high quality glass is actually heat treated and all these residual stresses are removed, so that there will be no hindrance in the mechanical properties. Okay, this is how it started, and you see the graph on the bottom as well, the compressive and then tensile and then compressive. Okay, this is how the residual stresses are formed in the weld joints. So we have to go for the heat treatment to remove all these, uh, you know, residual stresses. And the final one is the metallurgical phase transformation. Okay, so this is also I have explained when you see the microstructure of the weld point. So basically, we have original workpiece edge, we have a melt boundary, and we have cores, and then fine recrystallized grains, and then we have originally work material. And if you see each state, so one is at the center, is it the liquid just getting solidified, and then the other one is just below the solidus line, and the other one is below that the actual little far away from the solidus line. So if you see the properties, the ductility will increase till this point and it will try to decrease and it will remain constant, because we have a bigger grains, bigger small grains, and then they are getting reduced in size. As well as the strength will increase. It is a very good topic. When ductility is less, the yield strength of the component will be more. So now, if you see this cross section, it is not a homogeneous material at all. So now the, if at all damage happens, it can happen because here or here, because they are of different ductilities and different strengths. So at the interface, always there is a chance for the crack to propagate easily. So that is all about this metallurgical phase transformation, and then we'll move to the questions. It is already 7, so we'll wait for some 5 minutes, take some break, and come back. We'll start the problem session.
audio problem is there, sir. Hello? Hello? Audio problem is there, sir.
Yeah, hello.
Yes, sir. Audio problem is there.
No, no. So we're just taking a break for 5 minutes. Then we are going to solve some questions.
Okay.
Yeah. Yeah. Let us continue. Yeah. So we'll solve in same manner. So I will give some time for you to solve. Then I will explain. So you can try to read the first and second question and give me the answer. Either you can speak or you can post your answer in the chat. Then I will discuss. Please go ahead. Yeah. Any guesses?
First question answer is B.
Okay.
Second question answer is A.
Okay. First question answer is B.
Yes.
Okay. Okay. Thanks. So, uh, yeah. So when you see this net shape process, generally we go for this investment casting. Okay, with this, so we also known investment casting as precision casting, in which we go for net shape process. Because in die casting, still we are producing the net shape. Still, there are some things that we have to be removed. Okay, so this gate, so this not gate, this uh, extra portion that has to be removed. In which is in investment casting, we'll just have to cut and we just have to trim, which is limiting number of steps compared to die casting. Okay. So the best option will be investment casting. If investment casting is not given an option, you can go for die casting. And the second question is cores used to form hollow interiors. The cast during the permanent mold casting are normally made of metals. Okay. But in semi-permanent mold casting, we go for this sand mixed with molasses. Same as mold material. That is also correct. then special case. So generally we go for option A, which is metals. Okay. So let us read the next set of questions. I take some time and then read. Any answers?
Does not sense.
Okay. Okay. Next. Okay. We'll see. So question number three: as the number of pieces produced by sand casting increased beyond 100, the cost per casting. Yeah, that is the correct option. So, I've explained to you in the economics of casting. As you can see, the slope of this sand casting, which is constant after a certain number of pieces. Okay. So next question is, um, the following building process fall under the so series solid state building process. Okay, first is arc welding friction. So you see the options. So arc welding is not solid state welding process. It come under this fusion welding. So option one is wrong. So you can directly strike off this option and then this option as well. Okay.
Friction resistance, friction resistance and diffusion when it will come.
Yeah,
Second,
yeah,
third, sixth. Yeah.
yeah. We'll see. We'll. So the second one is friction welding, which is correct. So we have to see that. So then ultrasonic welding is also correct. Then this resistance welding actually comes under this fusion welding. So fourth option is wrong. So this is wrong. So this is the correct option. Oxy-fuel gassing is also fusion welding. Then diffusion welding comes under this solid state welding process. Okay. So fusion, friction, ultrasonic, and diffusion welding are the solid state welding process. So if you have still doubts, so you can see this. You can refer this page. So on the right side, you see this solid state welding process. One is the diffusion, friction, and then ultrasonic welding. On the left side, we have oxy-fuel gas welding, resistance, and then arc welding. Okay. So option B is the correct option. I think we missed this slide in hurry. Oh, sorry. Oh, we missed a slide. Yeah, let us solve this fourth question as well. Just read the fourth question. I think we slipped a question.
Option C, first, second, and fifth.
Okay, thanks. Okay, any other answers? Okay, let us solve. So die casting process differs from other permanent mold castings in a way that in die casting the molds are made of tougher metal. So if you are not aware of what this means, just keep blank. Don't go in hurry. Basically, the molds are made of these cast iron or these steels, but we don't know the toughness of them. So let us keep for a constant. Then let us move to the next option. The molten metal is forced into the mold cavity under high pressure, which is the perfect statement. So option two is correct. So we can strike off this because it does not have two, and then we are left with three options. Ejectors are not used to take out the casting after solidification. This is the wrong option because ejectors are generally used to take out the casting. So option three is wrong. So we can strike out this as well. So we are left with two. Then let us see the next option. Only low melting point metals are used for casting, which is the correct option. So option four is correct. So we have option A as the correct answer because all the three statements in option A is perfectly true. So option three is not a viable option. Okay, option A will be the suitable answer for this question. And then fifth, of course, the point is correct because the production rate is higher. So if you remember in the bifurcation between these two types, that is hot and cold chamber die casting. So basically we are always saying low melting point metals. Okay, low melting point metals. This also, this maybe 600 brass and then magnesium is around some 470 something. Okay, so always we do for low melting point materials only, using some 420 tin, some 200 around some 200 something 300, magnesium around 470 something. Okay, so let us move to the next set of questions. Yeah, please read and provide the answer.
Fifth question answer is A.
Okay,
Sixth question answer is B.
B. Okay, good. Yeah. Any other answers or any other suggestions?
C.
Which question?
Fifth.
Okay, let's see. Yeah, sixth question. Okay. So when casting solidifies before completely filling the mold cavity, casting defect is known as. So it is very straightforward. That is Mishram. Because hot tears is like when there is unyielding support when during solidification. Cold set is when two interfaces are not fusing properly. And then shrinkage cavity occurs when there is no enough riser to fill the to provide the material during freezing. Okay, so the correct option is Mishram. We'll see the next question as well. The source of heat in thermite welding is so it's not electric arc, it's not electrical resisting heating, it's not chemical flame, it's an endothermic chemical reaction. It's a very famous thing. So basically, what we do in thermite welding is we put the say this is the component that is to be welded. For example, train track. Okay, then we put 1:3 ratio of aluminum and iron oxide powders. Okay, if it is filled with powders, then we start the initiation with some fire. Then, due to this exothermic chemical reaction, so it will be in completely molten state. Okay, then we remove the casing and then we finish it off. So there is this exothermic chemical reaction that is actually taking place, which will provide the heat, and that heat is used for joining the metals. So, so this is the Mishran. As you see that the first Mishran is caused when casting solder before completely filling the mold cavity. So this Mishran. I hope it is clear. So, so please go through the 7 and 8 questions.
Answer is A.
Okay, good. Okay, resistance welding falls under. So it's a straightforward question, that is fusion welding. So we have only very few types. Fusion welding, in which we use this resistance. As I said, this used to like also called spot welding, in which we keep two thin sheets, and then we apply this uh, like potential, so that the center will be like melted. So we call this nugget, like that melted portion, and then this establishes the bond. Okay, so that's the one. And then eighth question, I think I have already discussed. Then let us move to the other questions.
Ninth question answer is A.
Okay.
Tenth question answer is C.
Okay. Yeah. Any other?
Sir, tenth question answer is C. Third answer.
Okay. Okay. So let us read. Building failure occurs often at the. So this is direct question. That is heat affected zone. Always from heat affected zone. Away from heat affected zone, which is wrong. At the fusion zone, wrong. Weld interface, wrong. Okay. So as I explained, so we'll have these columnar grains here, very big grains. Then we'll have these coarse grains. Then after that, there will be small, limited, like fine grains, followed by the base structure. Okay. So here we have the heat source, and here we have the room temperature. So this interface is like the like say quenched kind of. That's why there are finer grains. When this is exposed to the heat source, there are coarser grains, because there is time for them to grow. Okay, then this portion is heat affected zone, and here we have this mismatch of mechanical properties. Hence, there is always chance that failure occurs at the heat affected zone. So the next question is, so this is correct option B. A. During solidification of the weld, welded lens tends to expand longitudinally while the base metal tends to contract. Okay. So what happens during this? So we'll have this tensile stresses and then compression stresses here. Okay. So next, welded lens tends to expand longitudinally. Uh, okay, and then while the base metal tends to contract. Okay. Then the next question, next option is the base metal cools off at faster rate than the welded length. Okay, but this is not then the next option. Heat is distributed non-homogeneously within the weld zone and the base metal. Okay, the final option, welded length tends to contract. Yes, welded length tends to contract while the base metal tends to expand longitudinally. Okay, see if you see this diagram that I have shown here. So this length try to shrink, and then due to this shrink there are tensile stresses develop, and then sheet tries to expand. That's why there are these compressive stresses generated in the sheets. Yeah, I hope that is clear. This is tangential, this is compressive. Okay, so the correct option will be D, because weld length tends to contract where the base metal tends to expand longitudinally. So let us quickly go through this. So if you see at the center, will try to compress, means shrink, because of the molten metal available. So it try to shrink. That generates tensile stresses in the belt around the vicinity. Due to this tensile stresses, it offers, so it try to bring it down, this tensile stresses. Then the this weld plate offers a resistance to the tensile stresses and it try to contract. And that is how what you see in the below figure as well. So initially we have a tensile stresses followed by the compressive stresses. Okay, that is what being addressed here also. Okay, that is building length tends to contract while the base metal tends to expand. So due to this contraction, we have the tensile stresses. Due to this expansion, we have compressive stresses. So the all other options will be wrong. So it basically it tends to not expand, contract. The base metal cools off at faster rate than the weld length. Now it cools a little slower. Heat is distributed non-homogeneously within the weld zone and the base metal. No, it distributed uniformly. So if you means I will simply show you simple welded joint how they certify. Okay. So assume there is solidification happening. So we have weld pool here, and then we come. If you draw a straight line, and if you draw a straight line, and if you take point 1, point 2, point 3 here, and then in this also, say 4, 5. So if you see try two diagrams like 1, 2, 3. 1, 2, 3. So if you see this 1, 2, 3 diagrams with temperature, at one will have high temperature and it will decrease with the time, and similarly 1, 4, 5 it will have like this. Okay, so you see the curve. So we have a very nice uniform distribution of heat, and then we can plot with the time as well, time for the solidification. So this is simple analysis that we generally do. So that is all about this solidification weld. Uh, so this is the all about this weekly session. So if you have any doubts, you can ask. I will try to see if there is.
So this study material are you going to share us?
Yes, yes. These slides are uploaded in the website. If you see on the left row, there is a problem session section. just click on the problem session section. You will be directed to one Google Sheet or spreadsheet. On the spreadsheet, there will be drive links. You can directly access these slides.
Okay, sir. Thank you, sir. Thank you.
So, so there used to be one session. Yeah, you can. If you have any doubts, you can ask. Or, I will. I'm trying to see if there is any question on uh, this casting cost analysis. I don't think I will find. I'm finding any. But if you find it, just try to solve some questions, so you'll be confident with the formulas. Yeah. Thanks for joining. If you have any doubts, we can discuss, or you can carry on with your work. Thank you.
Yeah, thank you. Thank you, sir.
Yeah. Yeah. Any doubts? Yeah, then so I'm going to end the session. If you have doubts, you can ask. So we'll wait 5 minutes, then I will end the session at 7:45 maybe. Thank you for joining. We'll meet in the next week session.